Okay, so after discussing about this array efficiency, here I have shown you an example for array of clover detectors. Right. Now see, let us consider a single clover detector. Roughly the radius is approximately 4 centimeter, 5 centimeter, and the clover detector is kept at a distance of 25 centimeter from the source, and along with taking the anti-coincidence sheet, overall the intrinsic efficiency, suppose this is 0.6 for the typing, just let us assume this value. Then using this you can calculate the value of P. Look over here, and this is what it comes out. Good. Let us now play with array. So let us consider this table. You see, so this is the number of detectors, and I have considered value. What are the values that we have considered? 5, 10, 20, 50, 100. Okay, in fact 100, more than 100 also exist. Just do a Google search on gamma sphere. It's an array, very interesting array which has been used for more than a decade, more than 2 decades. Okay, it's quite old array and it has got more than 100 detectors. There are other arrays as well. Now, so this is the number of detectors. This is the triple coincidence. So NP3 into P to the power 3. This is double coincidence. This is singles, and this is all the coincidences, including two detector coincidence, 3 detector, 4 detector, and so on and so forth. That means everything excluding the singles. Now look into this structure. Let us consider, say for the example, first the triple coincidence sector. Okay, see, when the number of detector is small, the value is quite small. As we jump from 5 to 10, we jump by a factor of 10 over here. See, approximately 1 into 10 to the power minus 5 to 1 into 10 to the power minus 4. Again, when we jump from 10 to 20, then again a jump of 10. 1 into 10 to the power minus 3. Next, when we jump from 20 to 50, you get, what is this value? This is much higher, right? And again from 100, we have got this 0.189. You see the same trend, but more larger value is observed for the double coincidence. But you must be saying, sir, why do we consider coincidence? Look into the value of the singles. It's so very large. But remember, in single spectrum, there will be large number of overlapping gamma rays. So these values are not of use. They are just values, you can see, but they are not of much practical use because of large number of overlapping gamma rays from large number of residual nuclei which are formed in a reaction, compound nuclear reaction. Okay, so this number is quite tricky, these numbers. You can say, okay, the value is good, but it doesn't help you much. In fact, when the number of residual nuclei is large and most of the residual nuclei which are formed, they have masses very close to each other, then what you see for nuclei which have got masses close to each other, say 35, 36, 37, 38, what happens is that in such cases, the excited nuclei, the excited level, and say for example the gamma ray exiting an excited level from one nuclei and another nuclei which is close in mass to it, they are almost same most of the time. So one gamma ray, say 111 keV is emitted from 35 chlorine, and another say 38 argon, it can have 114 keV gamma ray as well. So does this help us? No. What will happen is that because of this, even doubles coincidence, there will be scenarios where there will be overlapping gamma rays, and that is genuine. 112 keV gamma ray you can get from 3 nuclei, and they are all genuine coincidences. None of them are fake. Why is this happening? Because this is so. Nuclei which have got roughly same mass, if you study the excitation spectrum, you will see most of the time they have got identical, very closely like gamma rays. So how to get rid of this? The only way is go for coincidence, more number of coincidence. Say for example, if I go to 5, that means 5th coincidence, then the possibility of 2 nuclei having 4 identical gamma rays or very closely lying gamma rays is very small. And in the case of 5th coincidence, you will be able to separate the 2 nuclei, the gamma rays from the 2 nuclei. You understand what I am saying? So what I am saying is the importance of having higher fold coincidence data. Look over here. See, the ratio of the kth coincidence efficiency, k plus 1th coincidence efficiency to kth efficiency is what? K plus 1 divided by k, and this comes out to be proportional to n minus k into p, or this is proportional to n. So if we have more number of detectors, then higher fold efficiency data, the overall advantage is also greater, and this way we can do data cleaning. We can identify the structure much clearly than lower number of detectors scenario. You understand what I am saying? So, if there is a scenario, no, let me give you a different example. Suppose, in one case, we have got a scenario like 100 detectors, 100 small detectors. And another, we have got say 20 big detectors. Okay, now overall it is seen that the efficiency is very large for these detectors compared to these detectors. Overall efficiency is large. But if we are trying to study a nucleus which is emitted in a compound nucleus where large number of residuals are produced, then it is better to use this type of detector. Why? The reason is just now what I have explained. Because since there are more number of detectors, even though the overall efficiency is little bit lower compared to this case, because of having more number of detectors, the higher fold efficiency will be larger. So we will be able to clean up the spectrum. What I want to say is this. Try to understand. Suppose there are 2 nuclei, X and Y. They are closely lying nuclei. Here we have got gamma A, gamma B, gamma C, gamma D and gamma K. Some just 5 gamma rays, and here there are again large number of gamma rays. Out of this I am just discussing about this few only. Here again we have got say gamma A identical, closely lying to this one. So they are same. Okay, gamma A, say gamma C, then gamma L. Gamma N, gamma M and gamma B. Now consider this case. What you will see? You are seeing that identical gamma rays 1, 2, 1, 2. Then gamma C is here. Gamma C is here. Any more? No. So we have got 3 identical gamma rays. Right? So if I consider 4 detector coincidence, then what will happen is that one, suppose this one, and they are all coincident to each other. Suppose they are all coincidence gamma rays, all of them, and I am considering 4 coincidence data. Then what will happen is that they will all be coincident to each other, right? Now I want to study this nucleus. Why? Not this one. So what I do, in the 4 coincidence matrix, I put a coincidence conditions like this. For number 1, gamma A, gamma C, gamma B. If I do, then everything, this also comes. Then in the last condition, I put gamma M. Then what will happen? Is there any gamma M over here? No. So all the nuclei connected to this nucleus X, they will not be present in my coincidence data. And this will be there. Now this advantage we can exploit this only in the case of large number of array, not in the case of smaller detectors. You understand this thing?